Welcome back. This video will be about relativistic momentum, energy, but first we'll start off with velocity addition. So version of these notes can be found on Monday, May 25th. The velocity addition should be found on the Friday in the previous week. But once again, I'm going to direct you to this textbook that you should probably read. Goes into a lot more detail than what I'm going to get into in this video. Otherwise, there is a couple little videos that's pretty much worth watching because they have decent animation and they have a lot higher video production quality than this video is. So on that note, let's talk about some problems with velocity addition when we're getting to speeds near the speed of light. So in Unit 1, we looked at Galilean velocity additions where we're basically talking about relative motion, and we focused on a lot of airplane problems when they're traveling with wind velocities, or same thing with boat problems when traveling with water velocity or current, if you will, and how we have to add those together for an observer on the ground. And that's involving two-dimension motion. If we're talking about one-dimension motion, that's just a simple matter of imagine yourself in a car driving down the highway going 100 kilometers an hour. Maybe someone next to you is speeding, they're going 120 in the same direction. You would only really measure their velocity to be 20 kilometers an hour because at your frame of reference, you are at rest, and therefore the person speeding by you is really only just going 20 kilometers an hour. So that kind of idea of velocity addition. Now, so if I look at the screen here, as I regather my brain, if we talk about jets traveling, they go really fast. And when they fire their missiles, very often their missiles can be fired at ridiculous speeds in comparison to the jet themselves. So for instance, in this case, I have some really, really fast fighter jet. It fires a missile at 460 meters per second relative to the actual jet. And the jet is traveling 250 meters per second relative to the ground. So someone on the ground would say, hey, that jet's moving pretty quick. Someone on the ground would not measure the missile going 460 meters per second. Someone on the ground would witness both of these velocities added together. So you would just add them together normally, right? Because this is 460 with respect to what the jet was traveling at. So those get added together, and the person who's standing on the ground witnessing this would say that missile is traveling at 710 meters per second, because that's just nice, simple Galilean velocity addition. The missile with respect to the ground is equal to, well, you can see it right there. Einstein kind of pointed out a flaw with this when we're talking about speeds near the speed of light. So for that, let's kind of just look at this little weird scenario. Imagine we have a flying saucer. So flying saucers, in my mind, go at really fast speeds. Alien spaceships. How else could they have gotten here? I guess wormholes, but that's a different lesson for a much different day. So suppose you have a alien spaceship that is traveling at speeds 75% of the speed of light, relative to some little alien here on, let's just call this gray area the moon, or a moon, or just somewhere else in the universe. So this thing is traveling at 0.75 times the speed of light. It can fire a missile at 0.6 times the speed of light relative to the little flying saucer. So this is very similar to the last problem. If we just rely on Newton's equations, or Galilean velocity addition, if you will, we end up with a problem, because special relativity says that nothing can go faster than the speed of light. Light will always be measured at 3 times 10 to the 8 from all frames of reference, and absolutely nothing can go faster than light. So if I go back to just good old-fashioned Unit 1 velocity addition, we can see that something is broken. If you add those together, you get 1.35 times the speed of light, which tells you that person observing this missile from the ground would say that it's traveling faster than the speed of light. So that is not correct. So Einstein had to come up with a new method of adding velocities so that it doesn't break that golden rule of physics that nothing is faster than the speed of light. So not possible. We come up with a new system. This system is ugly. All right, there's a lot of V's and U's, and therefore it gets pretty confusing pretty quick. So you have to kind of make sense of what each of these letters mean. So U prime is the speed of the object. So in those last two diagrams, that speed of the object would be referring to the missile. So the projectile in that case, if you will, relative to a stationary observer. Well, when we say stationary observer, try to just picture someone just standing on the ground, right? Because obviously the person in the jet where the flying saucer is in a stationary state according to their own personal frame of inertia. So in my context in this little lesson here, stationary observer would be the person standing on the ground, not moving relative to the ground. So that's what U prime is, right? How fast is that missile going relative to the person standing on the ground? V is the speed of the ship or the flying saucer or the whatever it is relative to that same person standing on the ground. Okay, so that's what V is, and V is in two different spots. U is the speed of the object relative to the moving ship. All right, so that would be the speed of the missile, if you will, relative to the jet. All right, so if you're in that jet or flying saucer and you throw something or shoot something, that's the speed that you would measure inside the jet or the ship. All right, so U is how fast that missile would have been according to whoever's in the moving vessel. So if you can kind of remember those three separate terms, this shouldn't be too bad, but it's really easy to confuse all three of those in some form or another. If you just accidentally confuse V and U, it shouldn't be that big of a deal. It won't actually change the overall outcome. But if you confuse U prime with either of those two things, it's going to be bad. As long as you're not trying to solve for V and U, I should jump back on that statement. As long as you aren't trying to solve for V or U, confusing these two won't be a big deal. If you're looking to solve for V or U and you confuse them, that might be an issue. So just keep that in mind. I forget what C stands for. Okay, so let's just do a quick little example. I stole a little Mario Kart GIF. Suppose you have Luigi and he's riding up on a souped up cart going 0.36 times the speed of light, and he throws a red shell forward at 0.68 times the speed of light relative to him. How fast is the red shell going in the Earth frame? So in other words, suppose Mario's off to the side here watching this whole thing happen. How fast would Mario say the red shell is going? So this is probably the hardest part. Well, the math isn't exactly easy, but this is the hardest part, getting this part right. Figuring out which one's V, which one's U, and which one's U prime. So Luigi's cart is traveling at 36% of the speed of light. I'm going to make that V. He throws a red shell forward relative to him. So because it's relative to Luigi, I will automatically make that U. All right, so if we're looking for how fast the shell's going with respect to the Earth frame, we are looking for U prime. All right, and if you were looking for one of these other two, it's a little bit tricky mathematically, but at grade 12, you guys should be able to manipulate the equation around. Or go online, I have it broken down online, how to do it, I believe. At least I used to. Okay, so get the equation written out. All right, so there's no radicals in this one, so don't suddenly throw a radical in there. So V plus U all divided by your denominator. And again, don't bother taking these out of the percent of the speed of light. Leave it as whatever it is times C, because when you multiply those two together, once you input everything in, when you multiply those two together for your denominator, you're going to get a C square in there, and that C square will just cancel the C square beneath it. So those get canceled off. You don't have to worry about it. Add in the top two numbers, well, you just get 1.04 times the speed of light. Most of the time, I find in a lot of these questions where you're just trying to figure out velocity addition the first few times you go across it and learn it, most of the time your numerator is going to be greater than the speed of light. Not always, but most of the time. So you work it through, divide it over, and you end up with about 84% the speed of light, or 83 point, actually it's 80.834 something, I don't quite remember, but I rounded up. So that's what it is to three significant figures. I guess it should have only been two, so technically it would have been 0.83, because I don't believe you can round up twice. So that's essentially what you do. Very often, if it's given to you as a percentage of the speed of light, you don't have to go the extra step and find it in meters per second. You can just leave it as is. So there's a couple of extra problems in your workbook. I think I only put 3 or 4 in your workbook. It wouldn't be a bad idea if you go to that online textbook and go to page 1025 in that chapter that's posted online. There's a few others in there that you should probably try if you want to get really good at this stuff. So that's just velocity addition. Special relativity also had some consequences when it came to momentum and energy. in the sense that it kind of, again, turned Newtonian mechanics on its head. So momentum's a pretty simple one in the sense that it's two terms that you really deal with are just mass and velocity. But when you are going at speeds near the speed of light, you can't just say it's mass times velocity. You need that relativistic factor. And one of the main reasons is according to classic Newtonian mechanics, technically your relationship with momentum and velocity should just be linear, right? You should just be able to go up and up and up in a nice linear fashion. But when it comes to approaching speeds near the speed of light, special relativity says no, you can't go faster than the speed of light. So your momentum goes up basically to an asymptote, right? So it just goes up infinitely quick, right? Technically, if you can go up to an infinite speed in physics, then this would still go to infinity as well, but this would go faster because you actually can't reach the speed of light. And just as a quick little reference, I had to look this up. The fastest thing that we've ever created was the NASA Juno robotic spacecraft. Now, this is something that we could tangibly ride on, although I still believe it's too small for humans. But it got a gravity boost as it orbited around Jupiter, and it was able to go at 0.0002 times the speed of light. So it was basically, what if I get rid of that? So it'd be basically 0.02% of the speed of light. So that's the fastest we've ever really been able to go. We can accelerate particles too really fast, but not really larger vessels. So that's pretty hard for us to do. Relativistic momentum, therefore, is basically just your classical momentum multiplied by the relativistic factor, right? So nothing really too much new to learn there. It's just tacking on that gamma factor. And then that'll find the true momentum for anything that is traveling at speeds near the speed of light. So for that, usually we're talking about particles. We're not usually talking about large masses going at speeds near the speed of light. It's almost always referring to some kind of particle physics because that's when it really comes in handy to be able to calculate the momentum. So in that case, we'll talk about the electron, and it's moving at speeds of about 75% of the speed of light. Find its relativistic momentum and compare it to its classical momentum. So if I compare the two, basically I could just solve for the relativistic momentum, but the long way, and then I can actually figure out what the two are in the process. So all I just really need to do first is figure out what the gamma factor is. So plug in my 75% of the speed of light into the gamma factor, so where V is, and you just work that thing through, and you'll get approximately 1.51 for our gamma factor. Plugging that into your regular momentum, you take the mass of an electron. So mass of an electron can be found on the equation sheet from the start of the year that you guys were handed out. So 9.11 times 10 to the negative 31 kilograms, multiply it by 75% of the speed of light. So basically 2 times 10 to the 8. No, sorry, not 2 times 10 to the 8, 2.25 times 10 to 10 to the 8. In this case, you can't just leave your velocity as a factor of the speed of light if you want to have the units in kilogram meters per second, which is the normal units for momentum. There is the units for momentum that a lot of physicists would use, but that's something that you guys will get to later on. So plug that through. Basically, your classical momentum says that you would have 2.05 times 10 to the negative 22 kilogram meters per second. So that's your classical momentum. Factor in the relativistic factor, and you would end up with 3.1 times 10 to the negative 22 kilogram meters per second. So it sounds like a very small number, but again, remember that the mass of an electron is ridiculously tiny. So that is not unheard of for a lot of particles about the size of an electron or larger. Protons, neutrons, they might get up to 10 to the negative 19 or 10 to the negative 18, depending on what they're doing. But yeah, expect to see numbers like this, 10 to the negative 22. We're talking about things like electrons. So we know that momentum and kinetic energy are linked. If you compare what it is in normal classical Newtonian mechanics, right? Your momentum is just a product of its mass and its velocity, and your kinetic energy is also a product of its mass and velocity. The only difference is, for the most part, this is usually a linear graph, and this guy would be a quadratic, right? Because it's not just mass times velocity, it's half your mass times the velocity square. If you just even ignore the half, doesn't really matter too much. It's your mass times your velocity square. So it's still the same two inputs, right? So technically, you can take the integral of your kinetic energy, of your momentum, and get your kinetic energy, or take your derivative of your kinetic energy and get your momentum. So tie calculus into the mix, and these two are related. Classically, as you move to relativistic momentum, that's just a matter of tacking on the gamma factor. When it comes to your kinetic energy, it's not just a matter of tacking on the gamma factor. There's a little bit of, I call it ugly math, because it involves a bunch of polynomials and numerical sequences. So basically, it goes beyond the scope of what this lesson needs to be. I believe I have a dumbed down version of it online. If you want to look at it on the notes that I provided online, you can look at it there. But it's not just, the point was, it's not just a matter of tacking on gamma factor for your kinetic energy. So what we'll do instead is I'll just talk about how as you approach the speed of light, as your speed approaches the speed of light, your momentum technically goes to infinity. But what that really means is a lot of your energy, normally when you're going at slow speeds, a lot of the energy that you put into, say, your car, goes into speeding up. But as you approach fast speeds, a lot of the energy that you put into the system doesn't necessarily make it go much faster. In fact, a lot of the energy, they say, actually gets put into the mass. And that's where a lot of eyes kind of widen open and go, what? Because Einstein more or less said that there is a mass energy equivalence. A lot of the energy that you put into a system to make it go faster when you're at speeds near the speed of light, that energy actually gets converted into mass. There's a little bit wrong with what I just said there, but that can be worked out later on. So because as you try to speed up, if you have mass, basically, the more energy you put into it, the more massive your object becomes. And therefore, it's not possible for anything with mass to ever reach the speed of light. So right away, all the sci-fi movies are wrong. Try not to get too hung up on that. Enjoy the movies for what they are. All right, don't be that guy in the theater going, well, that's not how that would work. So just try not to be that guy. This is the equation that Einstein correctly derived to explain your kinetic energy. And so the kinetic energy would be your gamma factor, your relativistic factor, minus 1, multiplied by what is known as your rest mass. Because it turns out mass, has energy itself, right? Just for the whole sake of having mass, the mass has energy. And so that energy increases as the mass starts to move. So if the mass can be perfectly at rest, it would basically be its normal at rest mass, where no extra energy is contributed to it. So that's what this little not symbol stands for. MO is referring to its rest mass. For simplicity, most of the time people will get rid of that not symbol or the little tiny O that you see there and just call it MC square. But there's a difference between at rest mass versus in motion mass. So this I'll just call it the at rest mass. So yes, MO is the rest mass. Forgot I typed that in there, which basically means if you distribute this rest energy, right, MO C square, into this little equation there, you end up with your kinetic energy to be the gamma factor multiplied by the rest mass multiplied by the speed of light square minus the rest mass times the speed of light square. So this is known as the rest energy, just mass times your speed of light square. Which technically means if you manipulate this equation and bring this rest energy over here, that gives you addition of the energy for motion, which is your kinetic energy, with your energy that is at rest. And so therefore, this gamma factor times mc square is considered to be the total energy that any mass can have, and that will be a sum of its rest energy and kinetic energy. So that is kind of a big little breakthrough when it came to 1905 physics, because with this information, they were able to figure out why the mass of the elements on the periodic table are less than the mass of the sum of all their individual parts. So for instance, if you take oxygen and look at the mass of all the electrons, the 8 protons and the 8 neutrons, and you add all their individual masses together, so 8 electrons, 8 protons, 8 neutrons, add all their masses together, and then compare that to just an oxygen molecule by itself, not the diatomic, just one simple oxygen molecule, atom, if you will, you'd find that the atom of oxygen has less mass. And so that discrepancy comes down to this equation right here, right? And from that, we were able to unlock releasing energy and creating nuclear energy, and therefore we were able to also create atomic weapons, but that's its own little nightmare that I'll get into later, not this lesson. So your mass energy equivalence, this is the equation that Einstein is famous for. E is equal to mc squared, but of course your total energy tacks on this relativistic factor. Actually, most people will recognize Einstein for this part of the equation, just this part here is mc squared. Most people forget about the extra little part here that gets tacked on to account for relativistic motion, right? If it's not in motion, this is all it is, mc squared. Okay, one last question and then I'll stop this video because I'm rambling on. So an electron in a television picture tube typically moves with a speed of about 25% of the speed of light. In your old-fashioned CRT televisions, if you will. Find its total energy and its kinetic energy in electron volts. I'll get into electron volts at the end. Till then, we're just going to find both its total energy and its kinetic energy. So its total energy can just be found by, well, the gamma factor times its rest energy, mc squared. Your kinetic energy can be found by your total energy minus your rest energy, or again, gamma minus 1 times the rest energy. So there's two ways of going about this, couple of ways to go about it. I would personally find the rest energy first and just write that off to the side, because no matter which equation you want to find for total energy versus kinetic energy, you're going to have to deal with your rest energy, right? It's found in both equations, so you might as well just find that, write it down off to the side. So take the mass of the electron, 9.11 times 10 to the negative 31 kilograms, multiplied by the speed of light square. So 3 times 10 to the 8 squared becomes 9 times 10 to the 16 meter square per second square. So that's just a number to also put in your head. Multiply it through, and what you'll end up with is this base value for the rest energy of an electron. This is a constant, right? This is how much energy an electron has when it's at rest, not moving. Roughly 8.2 times 10 to the negative 14 joules. All right, so that's a constant. Most particle physicists and nuclear physicists just know this number off the top of their head. Right? I don't expect you to memorize it, but it is a significant number for later on when you're doing some of these problems. All right, tie in the gamma factor. All right, throw in the value for the velocity, so 0.25 times the speed of light divided by the speed of light quantity squared. Throw that in there, work your math through your calculator, and you'll get approximately 1.033 and change. So this is just a quick little simplify. Typically though, keep whatever numbers in your calculator because you have more steps after this. So all I've done so far is I've gathered the rest energy as well as the gamma factor. So at this point, I can either go straight to the total energy by using this equation, or I can use this equation and find the kinetic energy. Or once I find my total energy, I can just put that in here and subtract the rest energy, and I have my kinetic energy. So there's a couple of different ways to go about this. To find my total energy, I won't bore you too much with the details. I've just basically multiplied these two numbers together, right? And I came up with to three significant figures, 8.47 times 10 to the negative 14 joules. So it's just slightly larger because total energy is going to account for how much energy it has just for being at rest, plus the additional energy of your kinetic energy. So your total energy should be greater than your at rest energy. And therefore your kinetic energy would just be the difference between your total and your rest energy. The equation I used was gamma minus 1. So if I subtract 1.033 by 1, I get, well, this is what I would have got. So I kept a couple extra digits. So instead of calling it 0.033, I kept 3 sig figs once I subtracted that one. Multiply by the rest energy, and you get something a little bit smaller because you're not really adding that much energy to it with, according to your kinetic energy there. So last little step, I found its rest energy, I found its total energy, I found its kinetic energy. So the last part of this question is to show that energy in electron volts. Now, electron volts is a benchmark unit for energy. Kind of like back when you were in kindergarten and your teacher told you at some point, maybe not kindergarten, but at some point when you're young, you were told at some point that a brontosaurus weighs as much as 5 school buses, or maybe 10 school buses, or some random value like that. You had no idea how much a school bus weighed back then. You probably still don't know now. I know I don't off the top of my head. But it was a good idea to visually give you a benchmark as to how heavy it might be. That's kind of the same idea of an electron volt. It is comparing the energy of a single electron moving through 1 meter in an electric field of 1 Newton per Coulomb, or 1 electron going through 1 volt of electric potential difference. But we didn't quite get into electric potential difference, so for now we'll just talk about I'll relate this to electric fields. So the value for 1 electron volt for this benchmark is the equivalent of 1.602 times 10 to the negative 19 joules of energy. So this is an equivalent to an electron, right? So these electron volts just give you some kind of either multiple of energy of electrons or just some other relationship to it. So imagine this, if you will, for the electron volt. You've got an electric field going to the left on the page. If I have a little electron, it would go against that electric field because electrons go in the opposite direction of electric fields. So imagine this electric field having the strength of 1 Newton per Coulomb, and this guy moves 1 meter in distance. All right, so try to relate everything back to ones and ones. So I've got the distance tracked, I've got my energy, my electric field, and the energy required for that would be a product of its charge, Q, the electric field, times the distance. So it almost looks like QED. So that works out to be Q, single electron, so I'll just write down E instead of typing out 1.602 times 10 to the negative 19 coulombs, I'll just call it E. Electric field, if we're talking about the base value here, 1 Newton per Coulomb multiplied by 1 meter, well, the Newton times the meter will be a joule. If I factor in the 1.602 times 10 to the negative 19 coulombs, the coulomb from the charge will cancel off this per coulomb for the electric field, and you'll just be left with the units of a joule. So that's how you can convert an electron volt into a joule, if you must know. So in other words, if you want to convert from joule to electron volt, you would just divide by 1.602 times 10 to the negative 19 joules per electron volt. And if I apply that to all 3 of these, right, your rest energy would be converted into 512,000 electron volts, otherwise known as 512 kilo electron volts. And in this case, your total energy would just be 529 kilo electron volts, and your kinetic energy would be 16.8 kilo electron volts of energy. Very often, if you start looking through particle physics and nuclear physics, you will see that physicists stopped representing masses in kilograms when we start to talk about particles. In fact, they take Einstein's rest energy because, again, if your particle is at rest, that it's going to have a base fundamental amount of energy just for having matter, just for existing. So as I said before, this is pretty much a constant, which if we convert it into electron volt format, kilo electron volt format to be specific, we no longer represent a lot of our masses in kilograms. We just take our energy, so 512 kilo electron volts, divided by the speed of light square, and instead of actually converting this into numerical form, physicists just leave it, this constant, as a unit. and you end up with the unit for mass to be the electron volt per speed of light square. In this case, it's the kilo electron volt. You can get mega electron volt, giga electron volt. It really depends on how big it is. It's kind of like kilogram. So this would be the equivalent of your gram, if you will. Once you factor that in, of course. But that's kind of the whole idea of this. All right, so 512 kilo electron volts per speed of light square is kind of how physicists remember the mass of an electron if we're not using kilograms. And the reason why they like doing this is because you're not having to remember two numbers. You don't have to remember that the energy is 8.2 times 10 to the negative 14 joules. You don't have to remember that the mass is 9.11 times 10 to the negative 31 kilograms. You can just remember one number. And then you know the number for both mass and you know the number for both and for the energy. So keeps life pretty simple. Even though physicists like to make things hard, once in a while they like to make things simple. I don't really expect you guys to memorize this again, but that's just something for later on, depending on where you go next year or the year after. So try some of the problems from that textbook chapter that I told you to look through. You also have your problems from the Unit 5 workbook to try. And if you get bored, you can take Einstein's special relativity one step further and prove that your total energy squared. So your total relativistic energy squared is equal to your momentum times the speed of light squared plus your rest mass or your rest energy, mc squared. So that's something that actually comes up in quantum mechanics. But it's if you like algebra, it's a fun little proof to try to get into. I'll let you figure that out though. So on that note, that's really all there is to special relativity. That's the cheap 2-cent tour. Try some of the problems. Email me if you have questions. I imagine you'll have lots of questions. The math can get pretty complicated. There's a lot of radicals and exponents involved. So do email me if you have troubles, and I will stop talking because this video is long enough. All right, have a good one.